So this is going to serve as another example of writing out things like cell notation, predicting standard cell potentials. And then there's one new piece in this question. I'm going to switch the reference in my reduction table. Okay? So the reference is normally hydrogen. That was in the previous lesson. And I'm going to switch the reference to water. And because water shows up twice, I have to tell you which water I mean, and I mean the oxidizing agent water. So I'm going to start with the cell notation. That's the first question. So I have a standard lead. So I have to realize, okay, I have the word standard, so I have the lead ion and solid lead dash dichromate cell. Okay? And the word standard is applying to both pieces. So even though it only says dichromate, we have everything in this dichromate half reaction. Okay? It's a short form. It makes it easier to convey whole half reactions without writing out dichromate, acid, chromium, water. That takes longer. So let's identify what two half reactions that we have. Okay? With voltaic cells, we have a lot of shortcuts. We really just need the two half reactions. The higher one up will contain the OA at the cathode. The lower one down will contain the RA at the anode. Now, I already have dichromate blued marked on my table. The other one is lead, and I need to find lead solid and a lead ion. And it is at the minus 0.13 volts. Okay, lead becoming lead and lead 2+. So the higher up, it's going to be my OA at the cathode. My lower one down will be my RA, and that's going to be at the anode. Okay? So I'm saying I don't have to do a big list and write all the ions. I'm just using my table to guide me and quickly figure out what's going on. Okay? Now we got to remember the format of cell notation. Does anybody question? No, it wouldn't run, and you wouldn't make much money selling a battery that doesn't run. I could not give you, it's impossible for me to give you a voltaic cell that doesn't run, because if you have both sides, you always have an OA above an RA. It's impossible. Now, if we change and we don't do voltaic, then what you're saying is true. If I start taking pieces out, but it's not voltaic, and that'll be Monday's lesson. We'll talk about electrolytic cells that don't run, but they're not voltaic, they're not standard, they don't have both sides. Cell notation, what comes on the far left? Which, do I start with the cathode or do I start with the anode? Does anybody remember or need to flip back in their notes? Perfect, you have to start with the anode. Okay. Now I'm just writing this as a little note. You don't have to write that, but it's a good visual. Anode, cathode has to be the other side. So my cathode is going to be the higher up half reaction, has the strongest OA, and that occurs at the cathode. So that's going to go way over on the right. I'm going to start with the anode in my cell notation. Is there a solid in that lead half reaction? Well, there isn't, as the OA. The RA, yeah, is neutral solid lead. Okay. So that's going to act as my electrode, PB solid. Okay. That's where you're actually going to connect a wire to. That'd be the piece of metal that came out of your beakers in the lab. Okay. Next, I have to put any electrolytes. Okay. I have PB2+, and that's the only electrolyte in the half reaction. So that's all I need to put in for the anode side. Sometimes the electrolytes have spectator ions, sometimes they don't. They're both correct. On a quiz, I would mark both of them correct. Okay? On a test, you could see spectator ions or see them left out. Okay, so we're done with the anode. We've got to move over to the cathode now. I've got to put all the ions, not the count, just what ions do I have. So let's see, I've got dichromate, I've got H+, and Cr3+. Again, I'm not putting the numbers in front. It's just a list of what's in there. We don't add water to the list. These are all aqueous. There's no need to add in H2O liquid. Line to signify I've ended the electrolytes or any non-solids. Now I need something to connect a wire to at the cathode. And I do not have any solids. So I need to use one of those inert electrodes. Can anybody tell me an inert electrode? And I'll use whatever one you tell me. There's two options. Erica? Carbon. Perfect. So that's the one you'll see on Monday. You'll use a carbon inert electrode. So that is the cell notation for this standard lead dichromate cell. Now, if you look at the way it was written out, it started with the anode first and the cathode second, and that's the format you're going to see in your questions in the book. Okay, it tends to be the anode cathode, just like cell notation. So that would have helped us a bit more, but we really didn't need that. Okay, calculate the standard cell potential. So the oxidizing agent, that cell potential, okay, is going to come from the cathode. I'm not writing out the whole half reaction because I wasn't asked to. Okay? So I'm just not going to take this whole half reaction and write it out. But the standard cell potential is positive 1.23 volts. Okay, the cathode that has the OA. Okay? We always go the reduction potential at the cathode minus the anode. Okay? The anode cell potential, which we get from the strongest RA, that's the lower down half reaction. Okay? And don't flip it, just pull it straight from your table, negative 0.13 volts. Students will often just do this on their calculator if it's a multiple choice question. Okay. Make sure you subtract the two. So I put in a green subtraction. We have a positive number, and then we're going to subtract, and then we've got a negative number. I get a positive answer. I encourage you to put in that positive sign. It reinforces to me, the teacher, that you know it's spontaneous. 1.36 volts. Okay. That is the standard cell potential. Okay. We talked about the meaning of the standard, meaning having both sides. It also means you have to have 1 mole per liter of all the chemicals. Okay. If it's not 1 mole per liter, you're not going to quite have that voltage. Okay. All your solutions yesterday were 1 mole per liter. Okay. All those bottles in the fume hood. Okay. And hopefully from your lab, you got voltages that were pretty close to what you would predict from the table. Okay. Last, okay. So that's kind of a repeat from previous lessons. Now something new. What would happen if hydrogen wasn't the reference? Okay. What if something else was picked as the reference? Okay. I'm going to figure out, so this is the, I'll call this old, which is the regular volt reduction potentials. We're going to figure out these new potentials. Okay. With our new reference, which is water as our reference. We're going to see what happens if we have a different reference. So let's mark that in our table, figure out what I'm talking about. So I'm referring to using water as an OA as the new reference. So I've got to find it. It's way down low. It's just below the zinc. Okay. It's minus minus 0.83 is the reduction potential with hydrogen as the reference. Okay. We're going to switch water to be the new reference. Water is now going to be 0. Okay. That's what it means as the new reference. Okay. Now I'm going to copy some of this into the table, which will help explain it. So where's our water half reaction? So we have 2 H2O liquid plus, I would encourage you to maybe put this into your notes also, plus 2 electrons produces hydrogen gas, 2 hydroxides, and the reduction potential used to be 0.83 volts. And now we're going to switch this as a reference, which means it's now 0 volts. Okay, and we're going to have to readjust our other 2 numbers. I'm going to write those in, and we're going to readjust them. We have our dichromate, half reaction, and we have our lead. Now, I'm not going to write out all of these half reactions just to save time. Okay? If you're confused, I would write in, okay, this whole blue box and this whole blue box from your table, the dichromate and the H+. Okay? The top one was 1.23 volts. This one was minus 0.13 volts. That's the old. We got to change those under our new reference. We now have to figure out, here's our 0, how far up is our lead now? Okay. Okay. This minus 0.83 is now our 0, so it's above the 0. So the new reference is going to be positive. We've got to figure out how far up is that. Okay. Now the short way to do this without making it mental math is if you take the old reference and you subtract the new one, it'll determine this new reference voltage. So once you grab your calculators and do that, take the old reference and subtract away our new one. We're going to do that twice. We'll do it one at a time. Minus 0.13, subtract that old blue reference. And it'll tell you how far up you are. You should get a positive number, because you're above the new reference. .70, I think. Okay. This minus 0.13 is 0.7 above our new 0. So this is the number we're going to have to use, plus 0.73 volts. We got to do the same thing to the 1.23. Figure out what would this voltage be with water as our reference. Okay? How far up, if you're minus 0.83 and you go all the way up to 1.23, you have to go up to 0 and then up even more. Okay? But that same comment I made works. Take the old reference, subtract the new. 1.23 minus that old reference. And I encourage you to do that. .06. So this is 0.7 above our new reference. This is a little over 2 volts above our new reference. We just reset this scale. Now, you might be a little upset with me with this last part, but you need to learn this. What happens if we use the new reference? We take 2.03, that's what we get with water as the reference. We subtract 0.70. I'm not going to say the answer for a bit. Grab your calculator, do that subtraction. Okay. We're using our new red numbers instead of the blue reference that your table has. Did anybody calculate what the voltage would be using a different reference? It's the exact same thing. It doesn't change. That's my comment. You might be upset with me at the end. We did all this work and it didn't actually matter. Which is a good thing, because this isn't inherently zero. The water, the hydrogen, 2H plus 2 electrons being 0, we just picked it as 0. It sets our scale, but it doesn't matter. We could have picked a different reference. You could have picked hydrogen, you could have picked water. You're going to get the same voltage no matter what. Okay? And you measured a voltage in the lab. It didn't matter what reference you had in the lab. You're going to get the voltage that you're going to get. Okay? This leads to 2 possible questions. Okay? I'd make a note of this. If I ask you for the voltage with a new reference, okay? Voltage, and there's a new reference, okay? If it's the E0 cell, the voltage for the whole thing, do nothing. There's no point. You're going to get the same answer anyway. But if I ask you for one of those half cell E0 reductions, if I ask you for one of those red numbers, then you have to subtract the new reference off of it. So any question that you change the reference doesn't matter to the total voltage. Cathode minus anode, the reduction potentials. Who cares? Doesn't matter. But if I ask you for one of the pieces, it does. Pretty much, I'll guarantee you on your second quiz, you're going to get one of these 2 questions. You're just not sure. You might get the top, the voltage of the whole cell. You'll throw out the new reference. You won't care. If I ask you for just one of the halves, you'll have to remember to subtract. A lot of students like a formula. If you want to solve for that reduction potential, the new one, I'm just going to write out what I said orally. Okay? You take the E0 reduction of the old and subtract the E0 reduction of your new reference. I wanted you to see the subtracting the 0.83 before I try to turn it into a formula. So I'll just end. I'm not going to write down. If we want to know what would the top half reaction voltage be if water was the new reference, I'd take 2.87, subtract minus 0.83, and I would rescale this. So that's the end of switching the reference. Another sort of different style of question, still on standard cells and and predicting voltages. Okay. We've got another standard cell using the short from a standard scandium copper cell. And the cell potential was measured. A positive of the voltmeter, that would be the red wire from yesterday, was connected to the copper and read 2.36 volts. I give you the cell notation, and then the question is, what's the reduction potential of scandium? It's not in your table, you can't look it up. So we're asked for reduction potential. That'd be E naught, but not cell. E naught reduction. We're kind of asked for what number would be in our table if we could have looked up scandium, but it's not there. We'll have to solve for it. So we just have one mathematical relationship, the one we just used in the previous slide. E naught cell equals the E naught reduction at the cathode minus the E naught reduction at the anode. This would be from the OA at the cathode minus the RA at the anode. Now in a second, I'm going to start pulling the numbers down and figuring out, okay, 2 of the 3 we can figure out, and there's one piece missing. Okay. E naught cell, we'll start there. Well, that's given to us. I'll put the positive in just to emphasize this was a spontaneous cell. Now we kind of got to figure out if, which is our OA at the cathode. The E naught reduction at the cathode. Which is the cathode? Is it the scandium or the copper? It's going to be the copper. The cathode has to be on this side. You also have the positive connection went to the copper, okay? And the positive is always the cathode. The negative is the anode. So the cathode has to be the copper. Well, that's right in our table. Okay? That we can know. We just have to look it up. The standard copper, there it is. It's 0.34 volts. That's the reduction potential of our cathode. Again, how did I know it's a cathode? A, it's the second part of the cell notation, and B, we're told the copper was the positive, where the positive electrode was. That has to be the cathode. Okay. Minus, well, the anode is the scandium, and that's what we don't know. That's what we're asked to solve. Okay. So we have to rearrange this and solve for that question mark. Okay. Most students would want to put an X probably in instead of a question mark. And that's how you try to solve for X. If I rearrange this for X, so I'm not showing my algebra, I'm skipping a bunch of steps. My goal isn't to teach the algebra, so I don't want to take a couple minutes with that. But when you rearrange this you get 0.34 volts minus 2.36 volts, you get negative 2.02 volts as the reduction potential of scandium. You can easily do a check to see if you're right. If you take, 0.34 volts minus this number, you do get the E0 cell voltage. So this question was a different style. All you've seen me do before was look up each of the E0 reduction potentials and solve for the cell. If you're given the cell and one of these, you can solve for the other. Okay. Now, it's not part of this question. I just want to take this data and put it into the table. If you kind of think of where would scandium fit, minus 0.2. So it would fit right where I'm putting this blue line on my table on the wall. That's where that scandium half reaction would live. Okay? And you could ask follow-up questions of what would scandium react with or not react with, because you know its spot in the table. Okay? But that was not in this question. You will absolutely guaranteed at some point in your test, you'll be given data and you'll have to put it into your table and answer a question with it, which is why I want to mention this. You can take that and realize, oh, this is where it would fit. Okay? Okay. This side would be a really good RA. It's really low on the RA side. It'd be a horrible OA. The scandium 3+ isn't going to reduce very much. So that's it for this slide. This was a diploma question about 7 or 8 years ago. Okay? This exact wording was just stolen from a diploma that is now used as an example. Okay? So that ends voltaic cells. I've got a couple slides, but we're going to leave this notion of voltaic both sides. We're going to leave standard cells and talk about spontaneous reactions, the ones that might happen out in the pond back there. Or if you're at home and you start dumping all these things together, you pour in some Javix and bleach and chemicals, and you got a nickel pot. You can cause chemistry to start happening, and you don't even realize you're causing chemistry to happen. Okay, so that's kind of where we're going. Okay, and then we'll talk about how to prevent it. So cell potential under non-standard. Okay, we're not at SATP. We don't have 1 mole per liter. We don't have both sides. We've got whatever you happen to have. We'll first sort of start with voltaic cells and then leave SATP in standard conditions. Okay. Once a voltaic cell starts to react, SATP is lost. Any thoughts of that first standard, and there was a lot mentioned, they're not all up there, that would be lost when you start running a cell or a battery? Not the temperature, not the pressure, concentration. Once you start running a battery, you're not going to have 1.0 moles per liter anymore. You're going to start using it up. So as soon as you start running a battery, you don't get the voltage you'd predict in the table. Okay? The voltage will start to drop. This is not really a testable thing. It's just a connection to real life. If you look at voltage versus time, you start running a battery and the voltage stays steady at the first bit while you're at 1 mole per liter, then 0.95, 0.92. Okay? But eventually you start to see the voltage drop over time when you run the battery. And at some point the voltage will get so low, your phone says dead. It's not actually 0. It's just dropped below the threshold that your phone can work, or that the light bulb lights up, okay? Or the spinner goes round, or your drill goes round. Okay? So you're losing one of the conditions of SATP. Okay? Okay? You just need to realize the voltage will fall. If you have any significant deviations from SATP, you will not get the voltages in the table. Pardon? If the concentration goes down, you think of, let's just say you had a battery made out of copper. Okay? I can't think of any battery, but we've been looking at copper. And you have 1 mole per liter of copper, and it starts reacting. The copper aqueous ion reacts and turns into copper. And maybe you go 1 mole per liter down to 0.5 moles per liter. To recharge it, you run this backwards, and we'll talk about this on Monday. You start taking copper and turning it back into the ion, and you drive that ion concentration back up. Does that make sense? Okay. Now, this doesn't go back and forth spontaneously. If it spontaneously turns into copper, you've got to like plug a battery into the wall and put energy in to recharge it. So if you have a battery and that battery is at minus 20 degrees Celsius, you have an electric car and it's a cold Alberta winter, you're not going to get the same voltage out of that battery at minus 20 or minus 40. Or if it's really hot, batteries don't like being really hot, 60, 70, 80 degrees. Okay, electric cars have issues in Las Vegas in the summer because it's so hot. Okay? The same would be true with your drill or any battery. Everybody's probably had issues. You're outside and your cell phone maybe gets super cold. You have it in an outside pocket and it's minus 30 outside and your phone gets cold. It'll just shut off on you. When the battery gets cold, the voltage will drop. It won't work properly. You take that same phone inside and warm it up and your battery level might go back up, okay? Just because you warmed that battery back up. Okay. Some other issues that cause deviations very specific to voltaic cells. If you had any coating on the electrodes, so if you picked your electrode up yesterday and you handled and fiddled with it, you covered it in oil from your fingers, that would cause an issue and you wouldn't get the voltage that you would expect. Okay. Okay. If you don't have a proper salt bridge, your cell won't run optimally. So if you had a teeny tiny salt bridge that was 1 millimeter in diameter and the ions couldn't move fast enough, or you had a huge air bubble, you're really sloppy making your salt bridge, you don't fill it all the way up, you flip it over and you got this huge bubble at the top that blocks the whole thing, or maybe it blocks 95% of the tube. Okay? You're not going to, you either read 0 voltage or a very tiny voltage if it's not totally blocked. Okay? Last, if your solution is made out of a whole bunch of ions, so if a student messes up and doesn't pour our solutions back, it's half nickel, half copper, okay? You're not going to get the right numbers. And that's why we're very careful collecting those solutions yesterday. We asked you to just leave them on your bench, and we collected them to try to avoid cross-contamination. It has happened. We've had to throw out whole bottles of solution in the past. So those are all some issues that can cause big deviations. Last bit, we're going to talk about more of the outside cells. We talked about voltaic cells in this slide and talk about, you know, having some issues with those cells. Okay? Now we're going to fully leave voltaic cells and talk about spontaneous reactions. And this course really focuses on corrosion, rusting. Rusting is a spontaneous electrolytic, a spontaneous redox process. So corrosion is when a metal reacts with anything in the environment that causes a spontaneous reaction and makes the ionic form, which you don't want. You want the frame of your Honda Civic to be solid iron. You don't want it to be iron 2+. That's weak, okay? And looks really ugly too. You don't want the door of your car to be iron oxide. You want it to be solid iron or solid metal. And we're going to talk about lots of things that can react with metals and cause them to spontaneously corrode. Now I'm going to focus this discussion not on any metal but on iron. What would cause this reaction, iron to turn into iron 2+? Let me set it up first. Give me a minute. Okay. So I need to let you write, and then when you're done writing, we've got to figure out, okay, is iron going to be an Ra or an OA? And then where do we need to go in the table to figure out what would spontaneously react with it? Okay. So don't say it out loud, but maybe right above that iron, OA or Ra, if you can figure out which one it is. No, Amara, I know, is keen to answer, so I'm going to, is iron an OA or an Ra? Ra, correct. So neutral metals are always reducing agents. You could have looked it up in the table or remembered that pattern. So where is iron? Fairly low. It's in the negative 0.4 volt range. So iron is a reducing agent, and we want to have a discussion. What would work as an OA that's going to react spontaneously? We're going to look at the table, and then we have to think of, what's actually practically going to be outside in the environment. So again, I'm circling iron on the table. And I'm going to box out all the oxidizing agents that's going to spontaneously react. Where do I want to go? Do I want to look down or up if I want a spontaneous reaction? Up, above. So I've got to go above iron, and we're looking at all of these guys and thinking, what might you actually find outside? Okay. If you look at the top, you're not going to see any fluorine gas outside corroding your car. So I'm going to pause for a second, and I want you to go through and think of, and we're going to make a list of which of these would practically be found in the environment outside that's going to cause any iron that you put outside to rust. Okay? Now you can use normal weather events to add chemicals in. So again, build your list and we'll brainstorm in a minute. Okay, so let's get a few. We're not going to spend the time to get every possibility out, but let's get maybe 2, 3, 4 examples from students. So does anybody have a thought of a pairing or an individual OA that would corrode iron? Yep. Oxygen and water, is that somewhere here? What voltage is that at? Yeah, oxygen, okay, I'm definitely going to buy that. The atmosphere is full of oxygen. All it has to do is rain or get wet. So O2 and that's one reason we want to keep metals dry. When they're dry, they're much less likely to corrode. Okay, let's get a couple more. I'll try to get a different student for each of these. Any other thoughts? OCl minus. It would react. I'm just not sure whether you're going to find OCl in the environment or not. Maybe. I'd have to do some Googling and research. I'm not going to put that one down because that's not something that comes to mind. That's definitely out there. Yeah. Erica? Oxygen and hydrogen. Yep, that's definitely there. Is that one there twice? Yeah, there's two oxygen and hydrogen. So you have oxygen and H+. Okay. Definitely going to corrode metals. Now, the more concentrated the reactants are, the faster the corrosion. So this will definitely corrode it. If you have a very acidic solution with a lot of H+, you can see a lot of corrosion quite quickly. We may not have time this year. I should set it up as a demo. If you put a metal in a highly concentrated acid, you can destroy that metal in a very short period of time. Within minutes, you can corrode a lot of that metal. Now, you're not going to have 6 mole per liter acid out in the environment, so, but you could easily have a pH of 5 or 6. Okay, very definitely corrosive. Let's maybe get at least one more. So as I go through, there's a lot that we're not going to see. We're not going to see gold ions. If anybody sees gold ions, let me know. I'd like them. They're very expensive. Dichromate we're not going to see. We got oxygen and H+. We're not going to see mercury. Sometimes students will tell me nitrate and H+. There's not a lot of nitrates, but there are some nitrates in the upper atmosphere. The last one I'll highlight is H+ by itself is above iron. Okay. So all you need is acid. Okay. Even if you don't have the oxygen, it's going to be corrosive. Okay. So these are all things you cannot get near an iron-based automobile or an iron-based anything outside because it will corrode. So we're going to end with a slide and a picture. How are we going to prevent this? What do people do, engineers do, to prevent water from touching their car? Okay, because clearly you can't stop it from raining. Your car's going to get wet. That's a guarantee, unless you only drive it in nice sunny summer days. So this is a pretty big list. There's lots of techniques that are done. The first thing you do to prevent corrosion is you have an oxidizing agent and you put a barrier. Okay? That double line is meant to be a barrier like a paint. If the OA and the RA can't touch each other, they can't transfer electrons and your car is fine. Okay? So you might think the paint is on the car to make it look good. You're horribly mistaken. We do not paint cars to make them look good. Okay? They might make you pay extra money, but the paint is there to prevent corrosion. Okay? That's the #1 purpose. Okay? Sometimes I'd even put a plastic layer on front of my paint on the nose of my car to prevent rock chips from chipping the paint, and then water and oxygen get at the paint, get at the metal in my hood and corrodes it. Okay? So we paint things, #1. Second, there's other preventive coatings that we use other than paints. And I want to talk about galvanizing nails. Okay? We coat things in zinc sometimes. Okay? When zinc rusts, it rusts rock hard. It makes a coating. You can go to Home Depot and buy an iron nail. Do not build anything outside of iron nails. If you build your deck out of iron nails, in probably 8 to 10 years, your deck will fall apart. Okay? But it could potentially kill someone if it's up high enough. Those nails will corrode, they'll shear right off. Okay? You're either going to use stainless steel, or if you've ever heard of galvanized nails at Home Depot, they've covered those nails in zinc. They've put a coating. Okay? That black is zinc. The zinc prevents water, acid, any of those OAs that we discussed from getting at the iron nail, and it keeps the iron structurally sound and keeps it strong. Okay? If you build a bathroom inside a house, you typically use galvanized nails because you could get moisture and water going into your wall. Certainly outside, you'd use galvanized nails as a coating. Okay? So that kind of ends the coating section. You paint it, and I'm just talking about galvanizing as an example. Zinc coating something. Okay. Okay. Another example. Okay. We're really going to use some chemistry with this one. Cathodic protection. Protect the cathode. Or use a cathode. Okay. This involves connecting a battery to the metal. Connect battery to metal, and you better do it the right way. Okay? You need the negative terminal to the metal. You're going to force electrons to the metal. You're trying to force the metal to be a cathode. When you connect the negative terminal of a battery to the metal, you are not letting the reaction spit out of electrons. You're forcing electrons at the metal. You're trying to make the metal gain electrons, which it won't do. Okay? But the key is you prevent the black forward arrow by forcing electrons at it. Again, the electrons can't leave, the reaction can't occur, and your metal just stays at a metal. Okay? This is often done to tanks underground. Okay? A lot of fuel companies, think Esso, Petro-Canada, if they want to protect a tank in the ground, they can connect a DC current to that metal tank, force electrons at it, and use cathodic protection to make that metal a cathode and protect it. Okay? The water is going to have moisture in it. Okay? The ground is easily going to be acidic. They're not going to prevent the OAs. Okay? They may not be able to protect that tank coating from getting scratched. Okay? But if they force electrons at it, they'll keep that tank from rusting. And that's cathodic protection. Okay? You better be a good engineer technician. If you're a bad one and you flip the battery the wrong way, and you put the positive terminal to the metal, you'll drive the reaction forward in a hurry. You destroy the whole tank the first night and be fired the next day and probably sued for the damage you did. Okay? So negative terminal will force it this way. The positive terminal will rip electrons away. We're not going to have time to do a whole lab on this, but I'll try to remember to do some demos. Okay? Almost done. Last main point. You can add another metal that will become the strongest reducing agent. Okay? So find something that's going to react instead of the iron, a better RA than the iron. Okay? You'll sacrifice that other metal and protect your iron. So what's hidden is a bunch of metals that are better RAs than iron. So I'll let you write, and when you're done writing, start looking below iron and seeing what's there that you could add in. I'll try to lift my table up. So there's our iron. We need to find metals. We got zinc is below. If I have zinc attached to a tank, the zinc's the strongest RA, not the iron. The zinc reacts, the iron's fine. So I got zinc, chromium, aluminum, magnesium, sodium, calcium, barium, potassium, and lithium are all metals that are better RAs than iron that will react instead of the iron. Now, any of those metals would work in theory. The one that works the best ends up being zinc. You want it to react, but not too fast, because you don't want to have to replace the zinc every day, and zinc's pretty cheap. So zinc is sort of the nice engineering compromise or trade-off. It works for the chemistry, cheap, not too fast, not too slow. Okay. Now your book has more information on ways of preventing corrosion. I went through most of them. It's not a bad idea to take a look at those 3 pages in your book. Now my last slide is a picture you're not going to take down. I just want to show you what this zinc coating or adding zinc to a metal object looks like. Okay. Now I didn't grow up in Alberta, I grew up in Nova Scotia. I've had 2 jobs. I've been a fisherman and I've taught. My dad was a fisherman, he had a boat. I've had to go to the boat store and buy big plates of zinc. Okay, I had to go one day and buy 70 pounds of zinc to attach to his boat. Okay, boats in the oceans corrode way faster because oceans are full of salt, so it's filled with an electrolyte. So you get much more corrosion in salt water than fresh water. So every ocean-going metal boat will have hundreds of pounds of zinc attached to the hull. Okay, this is just something I stole from the internet. It's not my father's boat. All of these white specks are zinc. They're all sacrificial anodes. Instead of the copper water pipes or the iron hull corroding, the strongest reducing agent is going to react first. The strongest reducing agent is zinc, not iron, not copper. Okay, the zinc on the hull, is going to protect any metal above it. Okay, once all the zinc is gone, boom, it's going to start attacking the iron. So you've got to replace this zinc yearly. Okay? But that's what that last example of a sacrificial anode looks like. You don't have to cover the whole boat. Okay, it's just the OA is going to get at the iron, and you electrically connect the zinc and the iron together. Okay? Zinc loses electrons more easily, so zinc loses them instead of the iron. Okay? Now, you would probably think, okay, if both of these metals spontaneously react with H+, wouldn't both react? And the answer is they both don't react. Only the best RA reacts. Okay? And that's why it protects it. It's not everything below H+, it's just zinc. Okay? So that's the sacrificial anode. So we've completed voltaic cells. We've completed all the spontaneous cells that aren't voltaic. So you have a bunch of questions that you can pick through. Again, it's a fair bit of practice. The goal is to be prepared for quizzes. Some of these questions you could just read through and think about. Others you'd want to work out fully.